All right, so let's read the part about electric fields when an
Electric
electric
field.
charge.
When an electric charge is placed near to another electric charge, it experiences a force. The electric force does not require contact between two charges, so we call it an action at a distance force. It acts through space. The
Okay,
region
so
of
what does it mean?
space
So what it
which
means now? How do you
it
understand
means
action at a distant force? What does it mean?
it means like I don't understand what it's saying.
Oh, really? They say
Yeah.
the electric force does not require contact between the two charges. It means that the two charges do not need to touch each other. They don't need to touch each other.
What
It
do
can
you mean
be
by
a
you
bit
don't need
far
to touch
away.
each other?
Sorry?
What do you mean by you don't need to touch each other?
Why what? Say again, please.
What do you mean by you don't need to touch each other?
It say the electric force does not require contact. Contact here means you touch something. You don't have to touch each other for this electric force to happen, you know. They can just be a bit far, like for example, half a meter away, or they can be like just 20 centimeter away, for example. But they don't have to touch each other, you know. So that's why this force is called action at a distance force. So it acts through space. You do not need these things to touch each other, okay?
So we don't need to touch each other.
Like for example, um, you know that, okay, if you put two magnets together, it doesn't need to be near, but it doesn't need to be like touching each other, but as long as it's about like, like 20 centimeter, 15 centimeter or something, they start to attract each other, right? Do you know that? Of
No.
course you don't. Anyway, so just remember that electric field, the force does not require contact. They do not need to touch each other. As long as you are quite near to each other, you will see that force. Okay, just read again. Just read more here. The region of space. Hello?
Yeah, I'm listening.
Come on, just read it. We're on video now.
The region of space where an electric charge experiences a force due to other charges is called an electric field.
Mm-hmm.
If the electric force felt by a charge is the same everywhere in a region, the field is uniform. A uniform electric field is produced between two oppositely charged parallel metal plates.
Say again. Evenly spaced parallel lines. Okay, sorry,
Um,
parallel metal plates, right? Okay, so they say the region of space. When electric charge experiences a force due to other charges is called an electric field. So once you are quite near to each other enough,
mhm,
there will be a force you can feel. So you're inside that electric field. You will feel it. You feel that
mhm,
force. And if the electric force felt by a charge is the same everywhere in that region, then the field is uniform. Here, this is an adjective. Uniform here means the same strength everywhere. You get it?
mm, yeah.
It means that at all the points in that field, the strength of that field is equal, the same.
Mhm,
So a uniform electric field is produced between two oppositely charged parallel metal plates. So these are two metal plates you can see here. The gray one here, they are parallel to each other. Okay. And so the plates on top, it's positively charged, plus, 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 plus. And the plates down here, it's negatively charged, minus, 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 minus. Okay. Now, so in between these you have a uniform electric field. Why?
Uniform electric field.
Sorry?
No, no. Why?
Why inside of this field, every point in here is equal in strength? I mean, uniform electric field. How? Why? Because the distance between the plates are the same in everywhere in this field, right? Now, it can be represented by evenly spaced parallel line drawn perpendicular to the metal surface. This one is the red one here. Is perpendicular to the metal surfaces. Now, the direction of a field denoted by the arrows is the direction of the force on a small positive charge. Okay, if I have a small positive charge here and I put it in a field, yeah, of
Mm-hmm.
course, it's gonna be attracted to the negative plate, right? Negative charge plate, right? It's gonna go down here. And if you place a negative charge here, it will go to the positive one.
Negatively charged.
Yeah, to the
How,
positive.
how do you negatively charge something?
Sorry, say again.
How do you like negatively?
How do you what? Say again. Okay, very slowly. Okay.
Like how just now when you say negatively charged, how do you do that? Like
I
what do you
can't
mean
get
by that?
you. What do you mean? Okay.
Never mind, never mind.
Come on, just say it until because I know you have something in your mind you asking. Come on.
No, it's a question. It's just like a small question.
Okay. However, moving charges. Okay, just read this one. Moving charges are something.
Moving charges are deflected by an electric field due to the electric force exerted on them. This occurs in inkjet printer. The electric field lines radiating from an isolated positively charged conducting sphere in a point charge are shown in figure 35.11a. B. Again, the field lines emerge at right
Emerge at
angles
right
to
angle to the
the
conducting surface.
yes.
Like for example, imagine if you have a plate, but it's not exactly a plate, it's a sphere. Now it's not like flat, but it's a sphere. So the line of the electric field, they have to be this way, not parallel anymore, right?
Mm-hmm,
No. But still, this field line emerges at right angle, which is 90 degrees to the conducting
mm-hmm,
surface. Anyway, and let's move on here. If you have a charge, around it, there will be a field to
mm-hmm.
all the directions around it, like that. All right, so you have this question. Hmm.
It's hard.
Okay, let's just try this one, okay?
This one. Oh,
We have a checklist here. After studying this chapter, you should be able to describe how positive and negative charges are produced by rubbing. Like you rub
mhm.
two object together. How do you make those charges?
Mm, by rubbing it together.
Yes. So one material
One material.
will
Any
become
metal, but oh,
another. So one material will have more positive, one material will be more negative, isn't it? So that's how you can produce positive and negative charge from rubbing. You need to recall what like charges repel and unlike charges attract.
mm-hmm,
Mhm. Okay, describe how a conductor can be charged by inductions. Like for example, if you have a screwdriver, how can you make it into a magnet? And is it permanent or is it temporary? Come on, try it.
Um, okay. Once you rub it, and then after that,
Mhm.
mhm,
You just have to rub that screwdriver with a magnet, So the
mhm.
screwdriver will become will become what's it called? Magnetized. But that is only temporary. Do you remember?
Temporary. So it's not gonna be like, oh yeah, it's not gonna be permanent.
Okay. It's a thing. You remember if like you try to rub this screwdriver, this metal part, with the magnets, this screwdriver will become magnetized. So it become a tiny magnet of its own. And because of that, it can attract this screw, which is made of iron. Remember? However, the magnetization doesn't last forever. It will eventually go away, and the screwdriver will become demagnetized, remove, like de mean remove. Okay.
Mm-hmm.
Okay. So we talk about static electricity. Can you explain what it is?
Static electricity is an um, static electricity. It's a result of uh, not balance between negative and positive charges in an object. It's not balanced. It's not balanced. That's static electricity.
So just imagine an airplane or a truck moving on a road. It's rubbing the air. So what would happen to the truck or that airplane when it moves? Think. Come on, think.
Mm,
If an object like a truck or an airplane rub the air when it moves, of course it moves, it rub the air. So what would happen to it?
mm. What happens when you what? Can you repeat that again?
What happened to a truck or an airplane when it moves? Of
Let's say
course,
an
it's going to be
airplane.
in contact with the air, it's going to rub into the air, right? So they become magnetized.
Not what was.
So
Let's
of
still
course,
not
a lot of
understand.
charge is gonna linger on those objects, right?
Mm-hmm.
So imagine if you touch a truck that has been moved. Sometimes you get shocked, right? The same thing happens to like a door knob in wintertime. Door knobs, which are made of metal, Sometimes you get, you know, it shocked you, right?
It
These are
shocked me,
static
yeah.
electricity. So beside
Mm.
from that inconvenience, why is it dangerous?
Why is it dangerous? Because it can kill you.
What do you mean came to you?
It's like it can, I mean, not sure. I don't know. I forgot like some terms.
Imagine if a truck has been moving for a few hours. It has static electricity. And when it stopped to refuel at a petrol station, okay? When it stopped to refuel at the petrol stations, gasoline is extremely flammable, right? It's easy to catch fire, isn't it? And static electricity can is a kind of electricity. So of course it's dangerous, right? The whole truck can burn, you know? We talked about this one before. Did you watch the video?
No.
There you go. That's why you don't remember. Sometimes I wish my students could be more studious. Anyway, so beside from that danger, people can die because of static electricity. So that's why trucks need the chain. Not this chain. This chain is basically used for snowing weather, winter weather, to help these tires to
Most.
stick to the road more, to have more friction. What I'm talking about is this one. These tire chains that basically they just hang down to the ground. Okay. What is the meaning of these tire chains? We learned about it before. Come on. Oh, come on. Try your best. Why is it even there? Why do you need these chains? It is there because the static electricity is going to move down to the ground. Okay?
Most down to the
It
ground.
moves to the ground, so the trucks won't have much static electricity when it stops, isn't it?
Mm-hmm.
So it reduces greatly the chance there's gonna be a fire, isn't it?
Let's
It's
go.
understandable.
Oh,
The
I
same
get
thing need to
I get a
happen
small part
to
of it.
an airplane too, you know? But they need some other ways in order to remove the static electricity.
Mm-hmm.
All right, so explain what it means by an electric field. Can you do that? We just did it.
Electric field.
Yeah, what is that?
Electric. Electric field is physical field, like a field that surrounds parts particle part particles,
And
and it change charge the particles and affects force on each other.
okay, so basically an electric field is a field in which in all the points that field, the strength of an electric force can be felt equally, isn't it? So that's why it's called uniform electric field. You're not learning it. You don't remember. Anyway, let's
I don't find it easy to remember in school.
of course physics is never meant to be easy to remember. So that's why you need to rewatch the videos. Come on. All right, so let's do question here. Two identical conducting balls suspended. Can you read it? Can you read it out loud, please? This. Please, come on. We're on camera. Come on.
Um, I really don't know. It just went so far.
Come on, just read it first. Two identical conducting balls. Come on, read it first.
But it isn't in the system of the that's and to rest with the text that you before and of the vertical and point in. 325. This is 2 times 2. The balls are equally opposite. The one ball is, I think
It's
it's,
charged and the other
is
is
it A?
uncharged.
Is it A?
Okay, so we have two identical conducting balls, so they are identical, they're the same exact thing, suspended by nylon threads. So these are nylon threads. Come to rest with the threads making equal angle with a vertical. This is a vertical. And it will basically come to rest, so it will come at this point, isn't it? Now, which statement is true? This shows that the balls are equally and oppositely charged, or the balls are... Which one do you think?
Mm, it's either, it's either one of those.
It has to be A, because they will
I said
finally...
it's A.
Yeah, they will come to rest. So the balls are equally and oppositely charged. So it have to be minus positive, So that will come to rest. Like, let's imagine if one ball is more charged than the others. Let's say you have 10 charge over here and 20 different charge over there. They will not come to rest, all right? It doesn't come like exactly at this point. All right, good. Um, let's try number 2. Explain in terms of electron movement. Like, how do you explain the electron movement? What happens when a polythene rod becomes charged negatively by being rubbed with a cloth? So you rub a rod, okay, with a cloth. So how does the electron move from where to where? So they say that this rod is becoming negatively charged, isn't it? So it means that the negative electrons have to move from the cloth to the rod, isn't it? You understand what I'm talking about?
No.
Read again. A polythene rod,
Polythene,
a polythene rod
polythene became
become charged
charged
negatively.
negatively by
So
being
it means
rubbed.
it received the electron, isn't it? It received the negative. It received the electron from somewhere, right?
So also it loses the positively charged by the cloth.
Or it received electrons. That's why it's a negatively charged, isn't it? Where does this electron come from? It has to come from a cloth here, right? Because you rub it with a cloth. Does it make sense?
Yeah.
There you go. So how do you describe it? When rubbing a polythene rod with a cloth, the electrons from the surface of the cloth will move to the polythene rod. That's how you describe it. Okay, understandable?
Mm-hmm. Understandable.
All right, number 3. Which of the statements A to E is true? In the process of electrostatic induction.
Induction.
Okay, electrostatic induction. Remember what it is?
Mm-hmm. Yeah, I will do.
Okay, a conductor is rubbed with an insulator. So if you rub something with an insulator, what would happen? Would something happen? Or not at all.
Not at all. Yeah.
Because insulator will not conduct anything, isn't it? Will not give you any electrons or whatever, right? So even if you rub a conductor with an insulator, nothing would happen, isn't it?
Mm-hmm.
So what would happen if a charge is produced by friction, like you rubbing something with each other, so that is friction. And they will introduce a charge to another object.
Mm-hmm.
C, negatively and positive charges are separated. If they are separated, would that induce electrostatic?
Will it induce
If they are far away
electricity?
from each other, it means separated.
Mm-hmm.
Would they produce electrostatic induction if they are far away from each other?
No.
There you go. No. A positive charge induces a positive charges.
You will
Would
just
that,
connect to each other.
yeah,
No,
would that happen? Would that happen? Would this one happen?
no,
They will repel each other, isn't it?
yeah.
Because they're the same. Okay, electrons are sprayed into an object. Like
Also,
sprayed.
straight to an object.
Yeah. Would
It
that,
doesn't work like that.
are you sure?
Yeah.
So which one is true then? It's
Which
B,
one
isn't it?
from?
It's B, isn't it?
Why is it G?
Sorry?
So why is it G?
So it's B is the only answer, isn't it? You understand it?
Mhm.
Right, please, but please watch the video again. Oh my God, for God's sake. By the way, I think your dad wanted to talk to me last week, but I think he didn't have a chance, I think. Anyway, so we should move on to the next one here. It's called electric current. Okay, so often we see, okay, electric current. So we'll talk about effect of a current or a flow of something, and a flow of electrons. And what's the effect of that? We'll talk about the ampere and the coulomb. It's the name of another scientist again, another scientist here. And we talk about circuit diagrams, like drawing the circuits of electricity, you know. So we have series circuits and parallel circuits. And we
Mhm.
talk about DC and AC, direct current and alternating current, alternating current. Well, this one is actually one of the easiest
Mhm.
part in physics, to be honest with you. All right, can you read this one?
And electric the in the figure consists of moving an electric part. In figure 21, and the Venn
Van de Graaff
diagram
machine is working.
machine is
This is a
working.
Van de Graaff machine, isn't it?
What does the Van de Graaff machine do?
It's a generator of electricity. It generates electricity. It's like any kind of generator, you know, like if your apartment complex runs out of, there's a power cut, there's a blackout,
Mhm.
then the people in the management need to bring on the generator. Otherwise, you won't have electricity, isn't it?
So this makes electricity,
Yeah,
but
simple.
not a lot, right?
Enough for basic stuff, I think. Like for example, every hospital will have some generators because in case of emergency, you need some vital machines to work to save the patient's life, right?
Mm-hmm.
Otherwise, they would die because of a power cut, which is tragic and unnecessary death. Because you could have
Mm-hmm.
prevented it, you know, with a generator, isn't it? Now, um, so basically, they say an electric current consists of moving electric charges. So the charges, they have to move. And when they move, they create an electric current. Just simply like that.
Mm-hmm.
Now, effects of a current. An electric current has three effects that reveals its existence. How do you prove that an electric current exists? Because you cannot see it. It's too small to be seen, right? But if you put your hands, your finger into an electric socket, you will feel it. Don't do that, okay?
It's like you cannot see with your eye. Cannot see
You
with your
have
naked
like
eye.
you have a lot of shock. and you won't be you won't even be able to recognize things. It's an electric shock, okay?
Mm-hmm.
Now, it exists, of course, even though we don't see it, okay? Let's say, okay, let's do an experiment here. You have a circuit board, okay? And you have a two battery. These are 1.5 volt battery.
Much is 1.5 volt.
Mhm. It's very small, like yeah, like this kind of battery, like only 1.5 volt. It's really small.
Mm-hmm.
Okay, so this one is connected
For the battery.
to a lamp. So this is a wire, okay? They connect to
Oh,
lamp. This is a wire. They connect to a lamp.
because the wire is metal and it transport electricity to the
Of course,
lamp.
the wires are metal. Of course, these wires are metal. And to the right side, this one is connected to a solution of dilute sulfuric acid,
What
H2SO4.
what is dilute sulfuric acid?
Well, basically, it's just a solution that conduct electricity, okay? It's just something that conduct electricity, okay? You can use anything, like for example, salt, table salt, water. Salt put in water, it would work too.
Mm-hmm.
Anything as long as it conduct electricity, okay? Clear? It can be
Yeah.
anything that conduct electricity, okay? Now, so this one will be further connected to the battery itself, but this side, okay?
Mm-hmm.
So, of course, the battery, there will be a positive
Arch.
and a negative side, right?
Mm-hmm.
Just like a magnet. All right. So what would happen here when you dip this thick copper wires into these acid? Of course, it conducts electricity. So of course, the flow of electron will go from here, go all the way through the lamp, and it go back here and go back to the battery, right? So of course, the light will shine. It will light up, isn't it? It will lit up. It just lit up, right?
I'm trying to understand
Sorry?
how the I'm trying to understand when the finish like when the start point at 1.5 V, the left one it goes all the way down, and then to the diluted acid, how does it like go back?
Well, it's like the flow of electricity often go one way, like this.
It's going back. There's the minus in the battery when there's like the
You will learn it,
minus
okay? You will learn
because
it. You will learn that, okay?
okay.
Okay. And then there's some effects. So why would we use electricity? It can be used for heating and lighting, okay?
Mm-hmm.
So to heat up things, like for example, if you're in a very cold environment, you turn the heater on. Of course, it consumes a lot of electricity, and it heats your room up. You feel good. You don't feel cold. For lamps, it's the same thing. The lamp lights because the small wire inside the filament of the lamp is made white hot by the current. Oh, light bulb. Look at this one. So basically, these are the filaments that we talk about. These are little metal pieces, mid-metal wires
Mm-hmm.
in the lamp. So basically, when electricity pass through, they will heat up, isn't it? And produce a bright light. Of course, this one is only traditional bulbs invented by Thomas Edison. But we know that he stole the invention from someone, yeah. Edison is actually notorious for scandals because people say that he didn't invent them, but he used his money to bought invention from the other inventors.
Is that true?
I think yes, because he's not a good person. Have you heard about Tesla and Edison, right? You heard the story, right?
Tesla? Yeah, I heard the story behind
There's a
what
drama
Tesla.
between these two.
Yeah,
So
I think I
basically,
heard it before.
yeah, so basically the guy Edison here is a very rich businessman slash inventor. So he said that he invented the light bulbs and also DC, direct current.
Mm-hmm.
Direct current means like it only goes one way. It doesn't go like the opposite way.
Mm-hmm.
And between him and Tesla, well, at first, Tesla wanted to work for him because, of course, Edison's rich. He's a famous inventor, and also he's well known for his invention.
Mm-hmm.
And then Tesla say that, oh, okay, I found something called AC, alternating
Tran?
current.
Oh,
So it means that his current doesn't only go one way, it go backward as well.
but why not you just like sell the but like sell inventions without telling it how it works so that you can when they ask how it works, you don't know how to respond.
When they ask how it works, what?
Never mind.
Okay, but never mind. So we will talk about the filaments in here. It can be lit up and it made white hot by the current. So of course it will produce like lighting. However, one thing I have to tell you, these traditional light bulbs, most of the electricity, like 95% of that electricity is turned into heat. Only 5% turn into like light. So these traditional light bulbs consume so much electricity for that light. So these days we have these newer light bulbs, energy saving. It's much more efficient.
Mm-hmm.
Anyway, so what can electric current do? It can produce a magnetic field as well. It can become a magnet.
Mm-hmm.
So the plotting compass deflected when it's placed near the wires. Okay, let's just say that. Okay, here in this experiment, let's imagine that you put a compass here. And when you turn this system on, the compass will basically moves. The handle in here will moves. Why? Because when there's an electric current flowing through these wires, there is a magnetic field around these wires, right?
Mm-hmm.
And it affects the compass.
I see.
Mm. Now, also, an electric current can produce chemical effect as well. So it can turn something into another thing. Yeah. So chemicals. So check for something called electrolysis.
Electrolysis.
Electrolysis, basically, we can use this electric current to remove something. Like, for example, if this is water, okay,
Mm-hmm.
and you put like a positive, this is a negative side here into the water, and then put some salt in it, so the water will become conducting. It will be able to conduct electricity. Okay, turn the system on. And so basically, you will see clearly some gas start to form at the positive side and the negative side as well. So the water is basically changed by the current. It's changed by the current to H2 gas and oxygen gas. So that's the
Mm-hmm.
chemical effect. Okay,
Okay.
understandable?
Mm-hmm.
There's a lot of things you can do with electricity, but beware, it's dangerous, okay?
Mhm.
So there's a chemical reaction made by the current. All right. And also the ampere and the column. These are the name of those scientists. So how do you see which current is stronger than the others?
Which current is stronger than the others?
Yeah. So how do you know it? So we assign like units for it. So the unit of current is called the ampere, ampere or
Yeah.
ampere,
Mhm.
which is defined using the magnetic effect. So we have
Okay.
1 milliampere, amen, it's 1,000 of an ampere. So let's just say
Mhm.
1 ampere is equal to 1,000 milliampere, for example.
Many thousand.
So let's just say 1 ampere is equal to 1,000 milliampere. That's what I said.
Oh, okay.
Makes sense, right? Or you could just say that um, 1 milliampere is equal to 1/1,000 of an ampere. Does it make sense?
Yeah.
Okay, good. Now, so the current is measured by a machine called ammeter. So
I
the
mean,
meter and it's called ammeter. Ever seen something like this before?
I think so.
Yeah. So it's able to see like how many ampere is the current. So it's gonna be able to tell you how strong the current is. Ammeter.
It looks like a radio.
Yeah.
Yeah.
These old equipment. These are very basics, old equipment, yeah. And so this is a current is measured by the ammeter. The unit of charge is called a coulomb. Coulomb. C
Mhm.
is defined in terms of the ampere. So they say one
Mhm.
coulomb is the charge passing any point in a circuit when a steady current of 1 ampere flows for 1 second.
What is an ampere again?
Well, it's a unit of it's the unit of a current.
Current.
Okay. The ampere is the current, okay?
What do you mean by a unit of a
Okay.
current?
And then of course 1 coulomb is equal to 1 ampere second.
Oh,
So 1 coulomb is 1 ampere second. So it means that what? 1 coulomb is a charge passing through any point of circuit. When a steady current of 1 ampere flow for 1 second, how many charges are there? It's 1 coulomb.
alright.
Okay, just look at it for a while. Just look at it for a while.
I try. uh, It's very interesting. One sees if a chart of video
Okay, so we
passes
have
on
so
in
there's
one
basically the
place.
formula here. Just read it.
Wait one. Oh, before the electrons were discovered, scientists agreed to think current as positive charges. Can you move to the side? I can see the
No, but you need to tell me what is coulomb.
Column is 1 ampere per second.
Yeah, it's just like how many charges? Like let's say 1 million charges pass through.
Mhm.
Okay. Okay, so do you have this formula? Q is the charge in column, equal to I is the current in ampere, T is the time in second. So Q equal to I times T. It's a useful expression connecting charge and current. Okay, understandable?
Understandable.
Okay, circuit diagram. So
Circuit
you can have a
diagram.
lot of circuits, okay?
Mm-hmm.
All right, so they
Current
say
must
current
have
must have a
X.
complete path or circuit of conductors if it is to flow. Okay, so what does it mean? A complete path.
It must have a clear path.
What would happen if there are holes in the middle of a path? Would the current be able to flow through?
No.
There you go. So the circuit must be a complete path, okay? It has to
Mm-hmm.
be like interconnected, linked together. Well, there cannot
Mm-hmm.
be any point in which there's holes or stop, right?
Mm-hmm.
So wires, copper wires, are used to connect the battery, lamps, etc. in a circuit since copper is a good electrical conductors. We always use copper, you know. It's cheap enough. It's easy enough to produce in a large number. We can actually use silver or gold to conduct, but those things are super expensive, even though they conduct better than copper.
Mm-hmm.
Anyway, we use copper. Now, if the wires are covered with insulation, such as plastic, the ends are barred for connecting up. So let's just
Mm-hmm.
say wire.
Mm-hmm.
Okay. So inside of a wire, you have copper, like these things are copper. But why do we have to cover these with plastic or rubber? Why?
So that like you won't get stuck when you touch
There
tape.
you go. Very good. You understand it now. It would be dangerous if these covers become damaged, right?
Yes. Then you'll get stuck.
Like imagine if your cat chew on a wire, what would happen? They
The
would get
wire
shocked. They
will
would
not
get shocked.
function.
Sorry?
It will not shock. It will not function anymore, and you will get stuck.
Uh-huh. And also, like imagine if these wires are damaged somehow, um, and the outside is flaked or is damaged somehow, there could be leakage of electricity to the outside environment.
My mother always got this kind of charger, or it's like exposed to the thing without rubbers, and she just cover it with tape,
Which one?
like this kind of stuff here. She just cover it with tape whenever it's
Paper?
exposed. Tape.
Well, paper actually is an insulator, but it is very,
Uh,
paper. It breaks easily.
no, she used plastic. She
Uh,
used tape. Tape.
okay, it's good now. Okay, so the sign or symbol used for various parts of an electric circuit are shown here. So a line means connecting wires. So this one means the wires are joined together at this point, isn't it?
Mhm.
However, if you draw like this, it means they are not joined together. They're just crossing each other.
Mhm.
So if it's like this, electric current does not flow through all of them, right? Because they're not joined. Like for example,
Mhm.
why crossing each other?
Crossing each other.
Like this. Like for example, the wire they cross each other. You see, this one is cross each other. but it doesn't actually connect at all, right?
Mm-hmm.
So it means electricity cannot flow to this one or that one because they don't actually connect.
Okay.
Understand, right? All right, so
Mm-hmm.
this one, this picture, it means a cell or a battery. So positive and negative side, okay?
Mm-hmm.
And if you saw something like this, it means two or more cells. There could be a lot of cells, like for example, 8 batteries at the same time, for example.
Mm-hmm.
This one means there's a switch on, off, on, off. So if it's away like this, it's off. If it's connected like this, it's on, isn't it?
Right. Can I go to the toilet? My stomach hurts so bad.
Sure. Okay, let's do 5 minutes, okay?
And my stomach hurts so bad after this.
All right. So we were talking about these kind of symbols, okay? So this one is a switch. You can turn
Mm-hmm.
on or off, okay?
Mm-hmm.
So this one with an A here, it's an amp meter. It can be used to detect how strong or how weak your current is in ampere. If you see something on an X like this, it's a lamp. Or it can be drawn like this. But I think these days people use an X more. It's easier.
Mm-hmm.
All right, so you can see okay. So people actually know about electricity before the electron was discovered, you know?
Mm-hmm.
And before electron was discovered, scientists agreed to think of current as positive charges moving around a circuit in the directions from positive to negative in the battery. So people still believe in that, these days, and it's like a convention. People think that the electric current always flow from the positive to the negative side. However, this agreement still stand, is still, valid. Even though we know that the electrons have to move from the negative to the positive, right? Because a
Mm-hmm.
negative is the one where you have a lot of electron, isn't it? It has to
Yeah.
move from the negative to the positive. However, because people still believe that the direction of a current is from positive to negative, so disagreements still stand. It's called
Mm-hmm.
conventional current. The word conventional means traditional. Conventional, everyone agrees on that.
Mm-hmm.
Okay, we call it conventional current. And the directions in which positive charges would flow, electron flow, of course, is the opposite direction to the conventional current. Okay, like for
Mm-hmm.
example, look at this one. You have a battery here, 1.5 volt, an ammeter, a light bulb here. So conventional current would flow like this from positive, go through an ammeter, go through a lamp, and then go back here, right?
But when it go back, it's like why do we have need to pair a bar so that lets it so we can go back? Doesn't it just
What are you saying? It doesn't make sense. Can you say again, please?
like the plus and the negative like when the electricity passes through everything, why doesn't it have to go back to the six?
It has to go back, otherwise the whole circuit is not complete, right? It has to go back here. Otherwise, the circuit is not complete and there won't be a current at all. Okay, I just talked about conventional. This conventional current will go this way. However, if you talk about the real electron flows, it has to go this way.
Remember this, right?
Opposite.
Mm-hmm.
Understand what I'm talking about, right? There you go.
Mm-hmm.
Now, so sometimes you have a circuit that can be a bit more difficult to see. So these are the point A, B, C, D, something like that. Okay, so here you have two battery. It seems like two battery here. One
Mhm.
ammeter, two lights, or two light
Too
bulbs.
much.
Yes. So conventionally, the current has to go this way to the two light bulbs and go back here. Yeah,
Mm-hmm.
correct.
Mm-hmm.
But electron flow has to go the complete opposite,
Really?
the other way, the opposite, right?
Yes.
All right, just remember that. Now, so let's see if we have something like this. Okay, so you can see that in this kind of circuit, everything here is connected next to each other, right?
Mm-hmm.
So let's just say the battery is next to an ammeter is next to a light, and the light is next to a battery again, right?
Mm-hmm.
So it is called
Mm-hmm.
series circuit. Okay, series. It means the objects are right next to each other. Is in series.
Mm-hmm.
Same thing here. This battery is connected to an ammeter is to this light, and this light is to this light, and this light is next to this battery. So it's like
Mm-hmm.
a series like this. They are like that. However, you can have something like this. So imagine if an electric current flow from the battery go through the ammeter to this point, it had to split into direction, right? Understand what I'm talking about? It had to
Mm-hmm.
split this way through this lamp, or it has to go this way to this lamp P, right?
Mm-hmm.
Before it go back here and back to the battery, isn't it?
Mm-hmm.
This one is called parallel circuit.
Parallel circuits.
Yeah,
So it
parallel.
connects to two or more wires.
It's like from one main wire, it's split into several directions.
But doesn't it like give less electricity to the lamp?
Exactly, exactly. It will. You understand it now. You start
So
to
it's
understand it now.
divided by two.
Yeah, exactly.
So the more lamps, the more divided it gets.
Yes, exactly.
Oh,
You
okay.
understand it now. Good. You're starting to understand things now. Very good.
Mm-hmm.
How about this series circuit now? Let's just imagine one current will go from here, go to this lamp, but it also has to go to this lamp, right? It's the same current, isn't it? And then go back here, isn't it?
Mm-hmm.
Let's say the current will go here. It's the same current that go to this lamp and the exact same current that go to this lamp, right? So what does it mean?
Mm-hmm.
The current that go through this lamp on the left has the same strength as the current to the lamp on the right, right? Does it make some sense now?
Mm-hmm.
And the exact same current will go back here to the battery. Okay, excuse me, I'm sneezing now. All
Mm-hmm.
right. These are series and these are series and parallel circuits. So the current is the same at all points in a series circuit. So what does it mean? Let's say I have a 1.5 volt cell here, okay? And the ammeter, they show that it's 1 ampere, okay? At this point, the current is 1 ampere. At this point, the current is also 1 ampere, right? At this point, the current is also 1 ampere, isn't it? And that point
Yeah.
also, isn't it? So
Mm-hmm.
at all the point in a series circuit like this, it's the same current that flow through, right?
Mm-hmm.
So it means, what does it mean? It means that the current is the same at all points in a series circuit. Now, how about in a parallel circuit? You see, it has to split in different direction, isn't it?
Mm-hmm.
So it means the sums of the current in the branches of a parallel circuit will be equal to the current entering or the current leaving the parallel section. So what does it mean?
That means
So the current going to here will have to split into two, right?
okay, so
But however, when it go back here,
it connects into one.
yeah, it become one. So basically, the current from here to there and the current from there back to the battery is the same thing, right?
Mm-hmm.
However, the current at each of these branches is only half of what it used to be, right?
Mm-hmm.
You understand it now, right?
Yeah.
Correct. All right, it's starting to make some sense now.
Yeah.
All right, so we have direct and alternating currents. So there's a difference between them, of course. So DC, direct current, they say that the guy Edison invented it, but I don't believe it. What is always a conspiracy theory about this
But
guy stealing?
how did they find out that Eddie didn't um
Hmm?
how did they find out that Eddie didn't invent the light bulb?
I don't know. It could be because he actually bribed people, or he used a lot of his money to buy our people, you know.
If he bought the invention, shouldn't it be his?
Sorry?
If he bought the invention, shouldn't it be his?
To be honest with you, he is much more of a businessman than an inventor, I would say.
Mm-hmm.
And there's a reason why people hate him, I think.
Mm-hmm.
Anyway, so DC. So in a direct current, the electron flows in one direction only. So it means they don't go flow back. Okay? It will not flow back. Like for example here, the electron will go only one way, conventional current. They will
Mm-hmm.
not go back, you know. But for AC, they will just go up, down, back, up, down, back. It's like that.
Mm-hmm.
All right. So there's a graph for steady and varying DC as shown here. So this current is the exact same through time. It's still the same current. And if you
Mm-hmm.
vary the current, like for example, at the first time, you see the current is increasing. And then just go down, go up and down. So this is not a very stable. It's not steady current, DC.
Mm-hmm.
In an alternating current, the direction of flow reverses regularly. So, like, let's say they can flow this way, one, and then it reverses, and then it reverses again, and it reverses again, like that. That's why it's called alternating current, okay? So let's go up, down, one cycle, and then once again, something like that. Understandable?
Understand.
All right, good. This is a symbol for alternating current. It means like like this one. So what's the symbol for direct current? I don't see it. Strange. So there's something here. So there's a question. Why is there an ammeter?
For memory is this like one way.
Why is there an ammeter? The one to detect the ampere or something. Why is it even there?
Mm-hmm. I don't know. Uh, not sure.
Okay, an ammeter is there to detect the strength of the current for measuring DC. Okay?
Mhm,
Sometimes you need to know like how strong the current is. You need an ammeter.
mhm,
Now, so if you have an alternating current, it makes the pointer on the ammeter move to and from the zero if the changes are slow enough. Otherwise, no detection can be seen. So let's say that, okay, ammeter. So when you turn the current on, it's gonna be whoozoo. It's gonna be somewhere here. Okay?
mhm,
But if you have an alternating current, the current will change all the time. So it's gonna be up, down, up, down, up, down, up, down, up, down, up, down, up, down like that. It will never be in one place, right?
mhm,
Okay, that's what it means. Okay, so batteries gives DC. Just remember that. Battery will give direct currents, just one way only, okay? But
mhm,
generators can produce either DC or AC. All right,
mhm,
understandable?
mhm. Understandable.
All right, let's end it here because I'm sure it's a lot of things today already. Okay, let's just end it here.